Start recording. Okay, last class or last 2 weeks, we talked about permutation test. If you remember, we talked about bootstrapping. We talked about confidence interval. So if you remember, the permutation test was the one that we were shuffling, and then we were testing, and we were saying if this basically two distribution coming from the basically these two data coming from the same distributions, shuffling them shouldn't change the distribution. So we did that. That was basically permutation test, and another was bootstrapping that we talked. If, for example, you get a sample from the you when I study something, you get the sample, and then that's all the sample you have. So you were basically resampling your sample in order to study your data, right? That was bootstrapping. I just wanted to remind you that, basically refresh your memory about that. So today we're going to talk a little bit more about those: confidence interval, permutation test, A/B testing, normal distribution, and stuff like that. So yeah, last 2 weeks, I guess we talked about confidence interval. Basically, it's an interval of estimates of a parameter based on a random sampling. So we said you can basically define this range anywhere between 0 and 100. Okay, but usually what we consider as a reliable range is like 95%. That we call it like 95% confidence interval. But you remember, bigger means like a wider interval. If you increase the confidence interval, for example, if you say, okay, my confidence was 100%, it means, of course, all your data going to fall between that mean and max, basically between this confidence interval. If you say my confidence interval is like 5%, like 10%, it means 10%, you're sure that this data falls in this narrow, basically, interval. So the confidence interval is the process that generates the interval. It generates basically good intervals about 95% of the time. So we talk about this, but today we're going to say, for example, you can use a confidence interval for testing as well. So you can say, for example, if your null hypothesis is your population mean is going to be a certain number, let's say X, your alternative hypothesis would be your population means is not going to be equal to X. So the cutoff for P value, you set it the P value, then you say, okay, you conduct 100 minus P value. Basically, that P is your P value. Even if when you're talking about the 95% confidence interval, your P value will be set to 5%, it means, okay? So if X is in the interval, you can reject the null. And if X is in the interval, you can't reject the null. So let's see what we mean by all this in the code, as we do always. So let me run this. So again, I'm going to go through them fast. If you have a problem really getting this, please go back and check the notes and find out exactly what's happening inside any of these functions that I put it here. So the first one is basically calculating the bootstrap mean. If we get a sample, we say which label we want to basically consider. We define the reputation. Then what we do, basically, we do resampling, okay? You remember bootstrap was you get the resample your sample. And we said this basically get another sample from your sample with the same size with basically replacement true. So then you calculate the mean, then you basically append all the means, then basically return the resample mean. This the second function. Is basically what it does. It calculates the confidence interval. As you can see, if you remember, we had this function, basically percentile. You call it basically what you're doing here. You cutting 2.5% in your left, 2.5% in your right of the distribution, and you get this 95% in the middle. So last time we basically what we did, we used some real data. Let's now not use a real data, use something that I basically, we define a table here, okay? It's a coin tossing. But if I group them by the head, that basically you can see the number. For example, 133 times out of 175, 133 times is the head, 42 times is tail, basically. So if you see this, you can basically guess this coin shouldn't be a fair coin, okay? Because the number of head is like 3 times number of tail. And it is not a fair coin, but so we're going to calculate basically, we're going to see what's happening with this coin. So if you calculate the mean, okay, basically if I get mean, because all the data are 0 and 1, and this is the count. If I calculate the mean of this basically number, it means I get 103 times 133. Then I get basically the proportion of that in this table. What I get basically this 76% of my my data is basically head, right? That's what I get with mean. So if you see, for example, here, if I have this as one area, I get the mean, I get 60%, it means 60% of my data is 1. So just because this is just 0 and 1, okay? This doesn't return the same things always. So if I run this, you can see 33% of my basically values are 1, because they are just including 0 and 1. So by mean, in this example, you can calculate the proportion. And because 1 is head, so we are calculating basically the proportion of heads. So 76% is proportion of the heads. So if we call that functions with this table, so we get something like this. So what it tells us is approximately 95% this bootstrap confidence interval for population mean is between 0.69 to 0.82. So what does this number means? Anyone can share some insight? Okay, I run all of this. You see this table. This is my table of a flipping coin. Looking at this, you can say it's not a fair coin. So okay, I run this bootstrap confidence interval mean functions, and I get this. Okay. So by looking at this data, what can you say? Can any of you share some insight?
That the 95% of the population, it's between these two numbers. Well, the probability.
Yeah, that's what it means. Like basically, it means that by 95% chance you're gonna get, using this coin that is like apparently unfair coin, you're going to get 69% to 82% head, right? Is it clear so far? So, but if you consider a fair coin, by fair coin, you're going to basically expect to see 50-50%, right? 50% head, 50% tail. But you can I mean, as in this histogram, you can see 50% is not included in our confidence interval, right? So by just looking at it, so you can use this confidence interval for basically denying the null hypothesis. For example, here the null hypothesis of us could be our coin is fair, and then that's the null hypothesis, our coin is fair. If our coin is fair, then you expect to see like around 50% head. But here you can see there is 50% is not included in our interval, so you can say, basically you can deny the null hypothesis. Is it clear? Any questions so far? Okay. So that's another use basically for confidence interval. It's rational if you think about it. Okay. For example, in this case, it's much more clear what I'm going. I mean, it's simple case. It's simplified case. It's not a simplified, but it's a easy case. Okay, like a flipping coin. But you can see just by calculating this, I can say, basically I can reject my null hypothesis that the coin is not fair. So let's go back to the slide. So in last class, we talked about comparing two samples. So basically the same thing, that the things that we did last time was basically, the name is A/B testing. A/B testing is defined like you have two random samples, sample A, sample B. Then if you remember, that was the example that we did. We talked about Deflategate, about the game between Patriots and Colts, about the air pressure in the footballs. That was what we used as example. Then the question that we asked was, are they drawn from the same underlying distribution? That was what we were trying to understand in that example. So basically that is the A/B testing. So basically what you're trying to do here is trying to decide whether two numerical samples come from the same distribution or not. So that's called A/B testing. And the name comes from basically you have sample A and you have sample B. So you're trying to do test between these two samples. That's the name come from A/B testing. So so that was basically then for the hypothesis we said the null hypothesis can be these two samples are drawn from the same underlying population distribution. So the alternative would be these two samples are not coming from the same underlying distribution. That's what we did with that Patriot and Colts example, Deflategate. So in permutation test that we do, null is basically the two samples are drawn randomly from the same underlying distribution. If the null is true, that's the idea of the permutation test, as I mentioned earlier. If the null is true, if this is true, then all the rearrangement of the variables among the two samples are equally likely. So what we do for this, we compute the observed test statistic. That's basically the first one. This one is the observed test statistic, is the one that we really measure. For example, in that Deflategate example, this is the number that we actually observe by testing the real ball. Then what we did, we shuffled the attribute values and we recompute the statistic, repeat. So it means we shuffle, recompute, shuffle, recompute, shuffle, recompute. Okay, that's what we did in the permutation test. So to test the statistic, okay, basically a test statistic is a random variable that is calculated from sample data and used in hypothesis testing. You can use test statistic to determine whether to reject the null hypothesis or to basically you're not being able to reject the null hypothesis. So basically the test statistic compares your data with what is expected under the null hypothesis. So you can have basically two types of data. You can have, sorry, it's not supposed to be seen. If the sample are categorical, then natural test statistic can be a total variation distance. So it measures the difference between the distribution in the two samples. Do you remember this when we were talking about total variation distance? You remember this example that we had about the basically jury panels in Alabama? I don't remember what was the name, like Swain case in Alabama. That was the case that we were having this basically. We said in our county we have 26 basically % are black, 74% are from other races, but in the jury panel we had only 8% black, 92% other races, if you remember this. So if you remember what was the total variation distance, can you tell me for this? Like Sebastian, Serna, can you, if you remember, total variation distance?
Not really, no.
You don't remember? Juan Basilio? Do you remember Juan Basilio?
No, I don't remember, teacher.
Okay, so let me make it easier. Who remembers? So he can tell me. It was very easy. I mean, it wasn't complicated.
It's like the sum of the differences, but I'm not exactly sure if I need to subtract like. Well, I don't remember which value do I need to subtract and add the absolute values.
Yeah, basically, that you're almost correct. Yeah, that's the thing. I mean, if you just look at the name total variation distance, you want to know how much they varies basically. So what you did, you get the absolute value of basically this one, this value here, and this one. Then basically you divide it by 2. So for this one, total variation distance that we calculated was 18, if you remember. So that can be, for example, for categorical data, not just this test statistic, there are other test statistics, but one of them can be this total variation distance that we calculate. But if your samples are numerical, the one that we did, for example, about the baby weight, for example, last week. So it's often simpler statistic is just fine for numerical data. For example, you can use absolute difference between the two sample means or median. Maybe that's just enough for you to do some statistic on your data. Okay. Clear? So let's go and see what we are talking about. Okay, cool. So if you remember, we look at this very interesting table last week that we have the baby weight, okay, gestational days, how many days a baby is in the womb of the mother, maternal age, maternal height, maternal pregnancy weight, maternal smoker. So basically by this, there are like around 100, I don't know, 100 something data here we have. So that was the data we worked with last week, but we didn't really did much. So let's, for example, group this table based on the maternal smoker, okay? Because we have either you're a smoker or you're not a smoker. So if we group them, you can see we have 715 non-smokers, 459 smoker mom. So you can see we have a good number here, actually, if you consider the whole sample size that we have, okay, it's a good number, so we can do some reliable test statistic. So this this basically histogram, okay, basically the data that we are showing here is we put the maternal, we use the same table. We said where maternal smoker is false, and then we histogram the birth weight for the baby. Okay, is it clear? What is this data? This is the baby weight for the non-smoker's mom. So if we do the same for the smokers, so what we did here, now we set the smokers as true. So this is birth weight of the baby for smoker moms. So if we do, okay, what do you think here? Do you think there is a significant difference between the birth baby weight for smoker's mom, this one, and non-smoker mom? So you can see the range is same, the percent birth is like they are all set same. Looking at this data, this two histogram, what can you conclude? Let me make it simpler for you. This is the same thing we put basically overlay both on top of each other. What do you think? Anyone? Is there
Maybe
any
there is
significant
a
difference?
relation.
Pardon?
Maybe there is a relation, but I think
The weight
you
for
you,
the
you
babies
can be
from
sure.
Pardon? I didn't get it.
the weight from the babies that came from smoker moms have less consistent weights than babies that came from non-smoker moms, and in general they tend to be less heavy.
So you think there is a significant difference? I mean,
Yes.
just looking at it, you think yes? Okay. So let's. I mean, okay. By looking at it, you can see they're more like sort of shifted towards left for the smokers. It means left. It means like a lower weight. That's what it appears from the data. So let's do the basically numerical study. So here, what we do here is this basically, we get the mean, okay, we group by the smokers here, and we get the mean here. So for the basically non-smokers, the mean of the weight is 123. For smokers, the mean is 113. That's the mean, okay? So what do you think here? Again, now looking at this number, do you think that the difference is significant or? I see some of you are like shaking head, like saying like it's significant. So let's again recall this functions. If you remember, basically here what we are doing, we are calculating difference in the mean. So this is basically just this number minus this number, you get this number. Okay, that's we are not doing anything weird here. So you remember this is like basically this is what I'm calculating here is like that total variation distance. Okay, because here I have a categorical data. Okay, about non-smokers and smokers. So now what we can do with this number, okay, so you remember, okay, now you can see here, but what test we are going to use for this type of data? Anyone has any idea? So why I'm using permutation tests? I mean, anyway, you have already see this function's name. So why I'm going to use permutation tests to study them? Like Xian, can you answer that question? Ricardo, Daniel, are you still there? Can you answer this question?
Yes, but I don't totally get it. So
Okay, see, we have this data, right? This is the table we have. Okay, so we want to see if there any relationship between the baby birth weight of the babies and the maternal smoker status. If the basically maternal smokers are false, which is non-smokers, we get different type of birth weight or comparing with the smoker's mom. That's the question.
I
So what
believe
we
that Jose already answered that in the chat. I don't know if it is related.
I don't get it.
Yeah.
What? In the chat?
In the chat, yeah, Jose mentioned it that there were like 10 ounces. And so it was significant, the fact that it was a smoker or not.
Okay. Now I can see 10 ounces is approximately, yes, it is C. Okay. So now the question is why I'm going to use permutation test.
Because we have two different samples and we want to
Exactly, that's the idea. So yeah, true. So that the idea with permutation test is like what I'm going to do is now is going to basically shuffle this two. And I say if, for example, my null hypothesis here is these two numbers, okay, for smokers and non-smokers, is coming from same underlying distribution. So if that's my null hypothesis, then shuffling them, okay, around should result in the same, this basically what I see here should be including in that shuffling if I do it multiple times. So let's define this long function, which is permutation test. I'm not going to go through again, but I put all this description here. You can check it out later. But what it does basically, it does the permutation test and then it calculates the means. So if I call it now these functions, permutation test means with this table, baby, then what I'm looking at these two different data, birth weight and maternal smokers, I'm repeating it 1,000 times. And ounce is basically basically the unit.
You do that to get the p-value, right? And with the p-value to decide whether the null hypothesis is accepted or not.
Exactly, true. So if I run this, now this is what I get. Okay. So what can you tell me about this? So what do you think now? What can we conclude from this? This red dot is the measured. Okay, this red dot is this 9. Okay, that we measured from the real data here. The difference between these two means. So okay, let me make it clear. What I'm doing here in permutation test, I'm shuffling the data. Okay, let's say I'm shuffling the data, then I again draw this table. I get, for example, false and true, because now I shuffle, so I'm going to get different data here. Then I get the mean, then I calculate this value. Basically, you can consider it total variation distance between these two distributions. Okay, I do it, I get one number, I do it again, I get another, I do it again, another. So I'm repeating that 1,000 times, and I get all thousands of this difference between these two means. Because each time that I'm running it, I'm shuffling these numbers around randomly, of course. So then I get some distribution like this. This red dot that you can see here is the actual number from my table, which is this one, 9.2. And this histogram is all those 1,000 times that I reshuffle this data. So now what can you conclude from this? This is also basically the numerical value here.
In this case, I think that the p-value is quite significant because it allows us to reject the null hypothesis because they do not belong to the same distribution. They are from different distributions.
And like a plain English, so what you say the relationship between smokers and baby weight?
That it does have a relationship.
Okay. Yeah, exactly. So it means there is actually it's so significant. It's like extremely significant. The p-value is like 0. It's like this never happened by chance, right? This is too far from our random distribution that we did by permutation test, shuffling the data around. So it means there is a significant relationship between the maternal smoker status and the baby weight, right? Is it clear? Any questions so far? All clear? Okay. So now let's go back to the slide again. So there we saw basically what we saw there is like that number. Okay, we have the hypothesis, we have null, basically hypothesis, alternative hypothesis. What we could say there, we could say, okay, these two are different, right? That's what we conclude. But how we can say how big is the difference, okay? So if you think that the two underlying population means might be different, you want to know how different they can be, okay? So for this reason, so instead of just running a same different test, okay, what you can do, if so you don't make any hypothesis, just estimate the difference between two population means. That's another way you can do. You don't need necessarily to have a hypothesis all the time. You can just run it, okay? Because in the hypothesis, we say, okay, the null hypothesis is they are same. Alternative hypothesis, they are different, right? Then we run the test and we say, okay, they are different. That's all we are concluding, okay? We are saying they are not coming from the same distribution. So we are rejecting basically null hypothesis and we say they are different. That's all we say. So another way is like, you don't want to just do this. You want to say, you want to know how big is this difference, okay? So you just estimate the difference between the two population means without any even considering a hypothesis. You can do this by bootstrapping the samples and constructing a confidence interval for the parameters. So that parameter would be basically the difference between the population means. Let's see what we mean by all this. Maybe in the code is much simpler. Again, I'm defining this functions, which is bootstrap confidence interval mean. You get the table, you get the variable, classes, how many time repetition, and what is the basically the unit. So if we run the same thing with birth weights and maternal smokers, okay, we're going to get this data. Let's see what we get out of this. So that's basically output. So here, it's same thing that we run like here, okay, not much different. We're doing the same thing, okay. Here, you remember this unfair coin that we did? We said, if we run this, we have basically by around 69% to 82% of our coin toss going to be head. That's basically what we are saying here. So running that here is like we're saying is basically, you remember I called the function with the table baby in these two columns, birth weight and maternal smoker. So what I'm saying here is like 95% by that 95% confidence interval. The difference between mean is going to fall between 7.2 to 11.3. This is not the person here, okay? This is basically mean between the weights. So that's again the explanation that I just give you is not everything perfectly fine. But what you can tell me about this? You remember this is the basically the value that we have. This is the weight, okay? This is the difference between means of the weights between smokers and non-smokers for the baby weight, okay? So what I'm telling here is like by 95% chance, okay, there is going to be 7.2 ounce to 11.3 ounce difference between the baby weights of smokers and non-smokers. Right? I didn't put any hypothesis here. I don't have any clue what's happening. I have the table. Okay. Let me allow baby. I have this table, okay. And I have no hypothesis. I'm going to calculate this only. Okay. I want to see what is the difference in the mean between the birth weight of the babies from smokers and non-smokers, right? So that I calculate it, then I see these results. So just looking at these results, I mean, okay, let's say if there is no relationship between the smokers and non-smokers, what do you expect to see here in this one?
If there isn't a difference?
Pardon?
If there isn't a difference?
So you're going to see Yeah, there. So what do you expect? Let me see what I can do here.
Between 0 and 1.
So, okay, if this is the basically, if there is no difference between these two distribution, what you expect to see is maybe you expect to see if this is your 0, okay, there is no difference. This is your minus side. This is like plus side. Because anyway, you're doing this 1,000 times. You're using bootstrapping. You have the samples. You're sampling. You're calculating difference, sampling, calculating difference, sampling, calculating difference. So most probably, what you expect to see is some sort of like this distribution, something like this, right? Because anyway, it's a random sample. There are going to be some babies that are heavier. Even if you look at this, okay. There are, of course, babies that are heavier. For example, this particular case here, okay, than these cases for non-smokers. This is a smoker, this is non-smokers. So there are cases, of course, that baby weight is heavier for smokers comparing to non-smokers. But you are not just looking at one particular example, right? So there would be cases here, if you expect there wouldn't be any difference between these two situations, you expect to see 0 in your interval. That's the whole idea. The 0 should definitely appears in your confidence interval, because there shouldn't be, I mean, because you expect not to see the difference. So 0 should be included in your confidence interval, but just looking at this data, the 0 is basically right here. The 0 would be around here. The 0 is not included in your confidence interval. So it means there is a difference, basically. Right? Do you get it? Because this is the difference between the means of the baby weight. But at some point, you expect to see that there is no difference. If it doesn't affect, if this doesn't affect the baby weight, you expect to see no difference at some point. So if we do the permutation test, we see them next to next, basically. That was the, oh, sorry, that's another test. So okay, this was for birth weight and maternal smoker. So let's look at another columns in the table. So about maternal age and maternal smoker. Okay, now I'm looking at these two columns, maternal age and maternal smoker, these two. So I want to see if there is any relationship between these two data now. So what can I do in order to detect that? Anyone? So same thing, same experiment that we did here. What we did here for this one. Okay, you remember we have this function now that we can call several times as much as we want and calculate the difference between different columns. And what is this function does is does the permutation test, right? So now we want to compare these two columns, maternal age, maternal smoker. Is there any relationship between maternal age and being a smoker or not? Basically, that's what it tells. Any idea? Anyone can share any insight? No? I mean, don't scared to say it. You already see that we run permutation test, right? We run permutation test. Now we're calling the same test with the maternal age, maternal smoker. Now we're looking at this too. Again, we're going to repeat the permutation test 1,000 times. and calculate basically the p-value, right? So if we run that, we're going to see this. This is the test statistic, percent per year. This red one is the observed statistic from my original data, the table. And then I did 1,000 times permutation test. I calculate the mean for that 1,000 times, and I did the histogram of that 1,000 times. You see this this distribution because of this absolute value that we have here. Okay. If I remove this absolute value, I run that again. Even you run this for baby weight and maternal smokers. Maybe that would be make it more clear. You're going to see this, okay? Because that I was taking the absolute value, that's why you see there this type of basically all positive value. But if you run it like this, you get this value again, it's still half. If I run that for maternal age with maternal smoker, if I compare these two situations with each other, then what I'm going to see is the same result. This is the observed value, this red dot. That's my observed statistic. This is the number. And then I calculated it. The empirical p-value is 1%. So based on this, now what can you say?
I don't think there is a relation.
There is no relationship.
There is a significant relationship, right? Because the p-value is 1%. It means it's hardly, basically, there's a chance that you see this data, the observed statistic, by chance, right? So it means this distribution is like significant. This observation is significant. What can you conclude from that? There is an association between maternal age, maternal smokers. That's all we can say, right? There is an association. You remember that association is the thing that they start talking from the second week. So there is this association between maternal age and maternal smoker. If we do the other one, the bootstrap method, for the same maternal age, maternal smoker, we're going to observe this. So here now you can go back to the point that I mentioned, like here, if there is no difference between this situation between birth weight and maternal smoker conditions, you expect to see 0 in your confidence interval. Okay, then you can conclude no, there is no relationship. By 95% confidence interval, you can conclude there is no relationship between birth weight for the babies and maternal smokers. The same thing here, okay? If there wouldn't be any difference between maternal age and maternal smoker, between these two, you expect to see 0 among your confidence interval, in this interval. But you can see that's not the case. 0 is out. 0 is here. There are some cases, but it's totally out of our confidence interval. Is it clear? That 0 you have to be seen. You have to see there because we are calculating the mean, right? We are calculating the mean. Then if there is no difference, the 0 definitely should be included in there, but it's not. So there is a relationship between these two data. There is an association. That's all we can say based on this. So let's look at another data again, maternal height and maternal smoker. What do you think before I run? I'm going to run, but before I show you, what do you think? What is the data? Maternal height, maternal smoker. So basically that the plain English is there any relationship between your height, let's say consider just moms, the height of the mom, and if they are a smoker and not a smoker?
I don't
What do you
think
think?
so for this.
I don't think so.
It's just weird, right? You think there is no relationship between your height and if you're a smoker or not. Let's see what we got. this is what we got. If we run the same test, permutation test, mean, baby, maternal height, maternal smoker, we did the permutation test 1,000 times. Basically, I forget this. The unit is inch, okay? So this is basically the test statistic that we got. This is the observed statistic. This is the empirical value, p-value that we got. So basically, it's like p-value is 0.24, it's like 24%. So what can you conclude from here?
That there is a strong relationship between the height and the how probable is that a person develops the habit of smoking.
So you say there is a high correlation between these two?
Since the p-value is 24%, I do think so.
No, so
I think
you remember?
it's the other way around, no? If it's less than 1%, you can take out the null value, but in this case, the null value is that there is no relationship or it was the null value that there is a relationship?
Okay, here, the null hypothesis, let's say, I'm not saying because I think it's too clear, the null hypothesis here, I'm saying these two data, these two numbers coming from same underlying distribution means there is no relationship between these two. There is no association. So I'm running like the same thing here. I said, I say there is no relationship between maternal age, maternal smoker. That's my null hypothesis. Okay, there's no relationship means they are coming from same underlying distribution. So I expect to see basically, for example, here I expect okay, forget that. So I'm saying they're coming from the same underlying distribution. That's my null hypothesis. Then I run the permutation test and I see this value. This is my observed, this yellow, the red dot here. Let me make it bigger. The red dot here is my observed statistic. The real data that I observed in the table. This histogram coming from my distribution, my permutation test that I did 1,000 times. So here I get the p-value 1% or 0.01. If you remember, we said if it's less than 5%, it means this test is basically this data is significant. If it's less than, what was that, 1% or 3%, like they say extremely significant. This is like extremely significant. So it means there is actually association between maternal age, maternal smoker. So what I'm doing here, I'm rejecting my null hypothesis. My null was there is no, okay? But what I see from this, I say, oh, okay, this rejects my null hypothesis. Okay, so just try not to confuse this. So it's the same thing I'm doing here. My null hypothesis is there is no relationship between maternal height, maternal smoker. They're coming from the same underlying distribution. Then what I do the permutation test. For each test, I'm calculating the mean of basically the height, okay? So again, I repeat that. For here, what we do, we say, okay, this is a maternal smoker, 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 non-smoker, non-smoker, smoker, non-smokers. Then I shuffling these values that they have randomly. Let's say I shuffle this value, the height, the maternal height. I shuffle this, I append this again with my table, then I do the calculation. I get the mean for the smokers, non-smokers. One time I do that 1,000 times. Then what I see, this is what I see. So this is my observed statistic, the red dot, and I see my p-value is 24, is 0.24 for 24%, whatever you like to call it. So it means it's not significant, right? For being significant, it should be lower than 5%. That's the basically rate that we put. So it means it's not significant. So it means my null hypothesis is true. There is no relationship between maternal height or maternal smoker. What it means in plain English, it means if you are taller, or if a mother is taller, it doesn't make her a smoker, or if she's shorter, it doesn't make her a smoker. There's no relationship between these two. Is it clear? Any questions so far? So Juan Salvador, did you get it? If not, if there is any question, you can of course ask. We can make it more clear, explain it more.
I mean, it's just that when I was looking around for how other people defined p-value, I found it, some people use it as the chance of our simulations or our tests matching the results we observed. So going by that, shouldn't more probability of them matching mean they are more significant?
No, that can happen. The thing is, if you're considering the significance, okay, let me again like say, what does it mean if when we say this data, this, for example, observation is significant? For example, this is what you observe, okay? So you go to outside in the street, okay, you observe something in the street, okay? So you wanna know how much is the basically chance that you observe that again, okay? For example, you go outside, you see a car flying, I don't know, okay? Then you say, okay, maybe that's just by chance. Maybe there are cars flying, it's just I happen to see one, you know? Then you go out 1,000 times, and in that 1,000 times, you never see another car flying, okay? So that one time that you see a car flying, if you were not on drug, okay, it means that observation was significant. It's not by chance. So it means there is something. So these things, what they do, for example, when they develop a drug, then they have a test group. For example, they have basically a group that they are giving the medication. They have a test group that they don't give the medication. So they want to know if this medication has any effect or not. So if you see, for example, this group that they receive the actual medication, the one that are basically under test, get better than this group that is not receiving basically the treatments, then what they say, okay, then they calculate this p-value. They say, okay, we did this, the p-value is like 5%, for example, or 4%. It means this medicine really affect. It doesn't mean this group by chance just get better. It means there was some effect of the medicine. It's not just by chance. This group get better, this group didn't get better. So it's not just chance involved. It means there was real things happening. Is it clear now? Or it was more confusing? It caused more confusion. So if you can calculate the p-value, okay, and it's very high, it means that basically observation is not significant. This data that you are looking at is not significant. It means just there is no association between them. So here,
if the p-value is still low, it means that the chance of, or the probability of an event occurring is very low.
It's very low, exactly.
At the same time, it means that if we do manage to observe that event happening, it shouldn't be due to chance.
I got it. I think where the confusion comes from. When we say the p-value is small, the probability, not the probability of the chance, the probability of the observation is by the chance. Okay, that may be more clear. When the p-value is small, the probability of this observation is by chance is very low.
Okay.
So you cannot just observe this by chance. That's what it means. If you observe this by chance, then you have to observe a lot, right? So why you observe very low number? That's the idea. So
okay,
here, what we're saying, if this probability is by chance, here for maternal height, maternal smoker, this is my observed statistic. So I say, if this observed statistic from my actual data, from my actual measurement, is by chance, so it should happen very often, right? It should happen quite often. And that's what I see. It's happening 24% of times. So it means it's by chance, basically. There is no
Okay.
Okay?
Okay, thanks.
No problem. So if we go do the bootstrap for the same data for maternal height, maternal smoker, let's see. This is what, again, I was talking here when I say you have to see the 0 there. If you see the 0, basically it means this is basically what it means. It means there is no difference in our population, basically, between these two. Because the 0 is there, it means the mean is 0 is in your confidence interval. So there is no association between these two data. Clear? Any questions so far? Okay, let's have like a 5 minutes break. Come back by 11:10, please. Okay. 11:10 sharp, please. Okay. Okay. So let's talk about randomized controlled experiments. Okay. You remember? I don't remember exactly what week it was. That example that we talk about Jon Snow and the case of cholera, that he was basically studying what is causing the cholera. And I show you the map of London in those days. And he draw the map, he draw like how many people are dying per houses. He draw this very interesting map in order to detect what is basically what causes cholera that that's killing people. You remember after his map, he find out there are basically all the deaths are was happening around that certain water pumps, okay? And then he concluded that those waters are causing cholera. So basically what we talked at that point that he could successfully establish basically an association between these two data. Between the water pump, it was like, I don't remember, it was like Wall Street water pumps, something like this, that he suggested, okay, let's remove the handles, and they removed the handle from the water pump, and people stopped dying. So what basically he could do up to that moment, he could basically, he could find an association, okay, the one that we were talking, association between this water pump and basically the death due to the cholera. But what he could basically, we said that was just association. That's all we could say about that. But he couldn't define the causality. Actually, that doesn't mean that could be a causality. So talk about causality. If you have sample A group as a basically a control group, sample B as a treatment group. If the treatment and control groups are selected at random, then you can make causal conclusions. So that's basically what happens when we're talking about developing certain new medicines. We have a control group, you have a treatment group. Okay, then you basically, if these two groups are perfectly chosen randomly, then you can make some causal conclusion by studying that. So any difference in outcome between the two groups could be due to first chance, then the treatment. When you're talking about, let's say, developing some new medicine, you have control group, treatment group, you're giving the treatment group the medicine that you're studying, the control group's receiving basically nothing or just fake medicine. Then any difference you see between the outcome of these two, then can be due to the treatment either, or by very low chance due to the chance, okay? So let's see what, what we're talking about here. So this, let me draw the table. This is a table, okay, of actually, this is the table about developing a drug for a treatment of the back pain for adult people. So what they did there, they basically divided their group. This is the real data. They divided the group between control group, treatment group, and they were studying the injection of botulinum. I put in my notes, botulinum toxin. Okay, that they were studying if this botulinum toxin has any effect on the back pain. That toxin is basically a protein that helps to stop muscle spasms. So they were injecting that into the spine of the people with the pain, and they were trying to see if that has any effect on the cure of the pain, the back pain. So they did it in a like randomized controlled trial. So basically what it means is like they take these two groups totally randomly. They didn't knew if they are part, basically the patient, they didn't knew if they are part of the treatment group or part of the control group, okay? And also the people that they were giving the medicine, they didn't know if they are treatment group or control group. So it was like basically what we call it like a double blind study. So they were giving the treatment group botulinum toxin, and they were giving the control groups like sodium solutions, which doesn't have any effect. They studied, this is the table, this is the output of the table. Let's shorten it. So this is the output of the table. So let's group them first. We want to know like what is the group. You remember by grouping here and calculating the mean, basically what I'm saying here is like 60% of this data are basically, okay, let me again tell it. I mean, this, let me remove this one. This one, one means like this particular guy got feel better after that. This one means this control group feel better. 0 means they didn't change their condition. Ones mean this treatment group feel better, they didn't feel better. So the 1 means there were some effect for getting better, and 0 means there was no effect for their treatment. So calculating this, we see like 60% of the treatment group felt better after the treatment, and 12.5% of the control groups, they felt better after this study. Is that clear so far? Any question? You remember again, because they are 0 and 1, and by taking mean, I can calculate basically the percentage here. So if we call the same function that we did earlier, permutation test means on this table, ETA table, which is this one. So while we are looking at group and results, okay, and we're running it 1,000 times. So this is what we get. So I want you to tell me what this means. Okay, imagine you're, there are of course medical scientists, maybe in the group they have a statistical stat people. You are one of them, they come to you with this table, they say, okay, we finished the experiment, this is what we got, so interpret this basically data. You say, okay, let me see what is the mean, like how many people are felt better in the treatment group, how many people basically in the control group felt better, what is the difference between these two. Then you run the permutation test. You say, this is my observed statistic. Basically, the observed statistic is this minus this. This is the difference between these two mean. And then you run your experiment 1,000 times using permutation test. And this is the histogram you get out of that. So looking at this, what do you conclude? Should they start mass producing that medicine?
I think so, because I mean the p-value is extremely significant. And that means that there's a strong relationship between the treatment and, well, the medicine for the treatment group.
Exactly. So that's perfectly correct. So it means if you see this is the observed value that you got, okay, and this is the rest of the basic experiment here. So you see this p-value is literally 0. It means by no chance, that's what it means. By no chance you could get this result. So it means, and if you remember what I showed you earlier here, no, what was that? No, this one. So what we did, we have sample groups, we have a control group, treatment group. Remember, still we are using A/B testing. The treatments and control group all selected at random. So we want to basically come up with causal conclusion. We don't want to say there is any there is association. We want to say there is a causality here. So if we did the test, so there is a difference between these two. That's what the data is showing us. So based on that, what we see, if there is a difference, it can be due to the chance, first of all, or it can be due to the treatment. So by the permutation test, basically what I'm doing, I'm reducing the part of the chance, okay? I'm saying, okay, I'm doing this 1,000 times. Let's see what is the chance there. And I see basically it's 0, let's say, okay? So by no chance I can get this. So it means what I left with, the options is this difference between the treatment and control group is due to my treatment, which means injecting that toxin into the spine of the people. That's why they feel better. It means this is significantly effective, basically, this medicine. Is it clear? Any questions? No? Okay, if I run that bootstrap means, you can see we get this. As I mentioned, 0 is totally out of your confidence interval range. It means basically the null hypothesis basically is not correct. The null hypothesis is, again, I highlighted, the null hypothesis here is there is no basically difference. That's the null hypothesis. I see no, the null hypothesis is not correct by this permutation test. Or you can do it by bootstrap test. So there are two different ways that you can come up with basically same conclusions. Here you see your p-value is extremely low, 0. So it means this observation is by no means is by chance. So it's very significant. So there is a causality effect of the treatment group. And here you see the 0 is out of your range. So it means it can't happen by chance. If it was happen by chance, 0 should be included here. Any questions so far? If no, let's move on. Let's go back to the high school math and talking about the average. It's basically that's your data. The average would be this. Of course, it's not a value in the collections. It need not to be an integer, even if the data are integers. So basically, your average is somewhere between mean and max, but not necessarily halfway in between. You remember, I mean, you know these things. Another thing to remember, the average is the same unit as the data. If I'm getting the average height of all the students and I come up with 1.7, that means 1.7 meters because my data was in meters. Then remember, averaging basically data has this smoothing effect, or smoothing operators. So it's collect all the contribution in one big spot, then split it evenly. So average is same with means. So you know average already, you know means, which is same. Then you already talked about the median. Even before I talk, you already knew about the median. So how you answer these questions? This is the histogram of all NBA players. The height, okay, this is the height and age. So what do you think here, looking at this histogram, what do you think? Mean is bigger or median is bigger?
Mean is bigger.
And why is that?
Because I think, well, I see that, for example, the mean is approximately 80 through 83 or something like that.
Okay.
I'm sorry, no, I'm making a huge mistake here. No, forget my answer.
So you want to change the answer, like median is bigger, or totally you're thinking wrong?
That I need to consider some other things. Let me just think about it a little bit more.
Actually, what you need to do here, you don't really need to add them up, or basically what tells you the answer is the way that the data is distributed. The tail of the distribution, basically. That, for example, looking at this data, the tail is like to the left or towards the smaller number, the tail of the distribution. Or basically what you can say is that the data is skewed to the left. So what do you think? Mean or median?
I think median it's bigger than mean. I think mean it's between 80, but median it's between 83, 84.
Okay, so how you you did the calculation, or you say it based on the shape of the distribution?
No, because, well, if it's an histogram, I can see that the median, well, it's at least 82, because it's the number that repeat more. The mean, well, I think it's because if the shape is to the left, I think it's to the left of the graph.
True, that's true. Jose Choza, I don't see you. Can you say that to everyone, the one that you just texted?
Yeah, I would say that median is bigger since it is not affected too much by the extreme values. The median takes like the most frequent value in the middle of the distribution, and the median is mostly used for skewed distributions, and the mean is mostly used for normal distributions.
Yeah, that's correct too. But okay, looking at this, so you can say, as you mentioned, median is bigger because the data is basically skewed towards left. So you can conclude it like this. If it's perfectly symmetrical distribution or it's perfectly normal distribution, mean, median, basically mode, forget mode, it's all falls in the same place, right? Mean and median would be the same for the perfectly symmetrical distribution. But when the data basically is skewed towards the left or smaller numbers, your median is bigger. As you mentioned, because median is less affected by the extreme values, of course, but mean is more affected by these extreme values. But if the data is skewed towards the right or toward the higher value, you can say the mean is bigger, because again, it's mean that is getting affected by these extreme values. Even if I put one, for example, here, just one very small number just at the end of it, it's not going to affect the median, right? Because the median is the middle of the basic our data. It's half of them are smaller, half of them are bigger. It doesn't going to affect it much, but it's going to affect mean a lot. So by just looking at how basically the histogram is skewed towards left, towards right, looking at the tail of this distribution, basically you may find out that the relationship between mean and median. That can come handy in some basic examples, some sort of distribution or data that you want to study. So basically the mean can be, if you're looking at mean, if you consider basically what they say, if you consider this as a physical object, the mean can be the balance point of the histogram. Basically that's, if it's something physical, you put your finger in the mean, basically it should balance your histogram. Again, remember it's not the halfway point of the data, the mean is not median. Unless the distribution is symmetrical perfectly, then the point is both average and the median would fall in the same place if it's perfectly symmetrical. So if the histogram is skewed, then the mean is pulled away from the median in the direction of the tail. That's the idea. Okay, just remember this. There is no code for that. So let's talk about the standard deviation. You know about it, of course, already. So let me see what okay, so what we talk about like so far, before I go there, we talk about mean and median. Whatever we are studying so far is we are studying. We so far talk about mean and median, and what we are doing with the permutation test, that bootstrap test, we are calculating the mean. But if, for example, let me notate. So as we mentioned in the previous slide, if the data basically is symmetrical, or if the distribution is look like a normal distribution, then your mean and median is going to fall around the same number. Okay, so it doesn't tell you much at that point, the mean and median. For example, as we mentioned, if this is the thing, if this is the normal distribution, your mean and median gonna fall the same place. Okay, so you need another basically another value, okay, to tell you more about your distribution. So which is basically what we're going to talk now is the standard deviation, which is basically going to tell you how a spread is your data. Okay, so it's going to measure basically the spread of the data, especially in the tail of the distribution, which mean and median doesn't tell you much about it. So in order to do that, you can do, for example, in order to measure these extreme values, you can say, okay, I want to get the biggest value minus the smallest value. That's how I'm going to measure that. But it doesn't provide information about the shape of the distribution, because even if your distribution is like this, still there are very big difference between mean and max, but it doesn't tell you much about your distribution. Or even your I don't know, the distribution could be the mean could be here, the max could be here, then distribution could be a lot of shape, right? So you cannot just measure mean and max and say conclude something about your distribution. So another idea is, okay, we measure variability around the mean. So we get the mean of our data, then we say how much our data varies from the mean. So then we need a way to figure out this data. Basically, that's the standard deviation. So before we go to the equation, even we want to talk about that in the code. So imagine this is the value, this is the array that we have. We have 3, 2, 9, 3. So this is the array that we define. So what we do first, we said we take the average of this. We add them up, we divide it by 4, so we get the average, which is 4.25. Then we said we're going to calculate the deviation from the average or from the mean. So what I'm doing here, I'm getting this, my value, and looking at each particular value, and then I'm calculating the deviation between my value and my mean. Okay, so that's the deviation. I append that to my table. So I get, this is the value, this is the deviation from the average. Okay, So then if I basically sum them up, if you sum the deviation from average, you always get 0. Okay, remember that. If you calculate the average or mean of your values, which is this one, then you calculate deviation from average and you sum them up. Of course, no matter what is the distribution, how many numbers, you always going to get 0, and it's very rational. Then what you do again, you get this deviation, you get the square of the numbers, you do the to the power of 2, you get the square of that, because it's not going to help us, right? If you sum them up, you're going to always get 0. So we need a way to make this positive. So we get this basically root, not root, but we to the power of 2. Then this is the basically a square of the deviation. We get the square value of the deviation. So you can see here, this is the value. We did the average, which was 2.2, 4.25. Then we did the deviation from the average. We did the square deviation. Then what we do here, now we get the mean of all these values. So we get the mean is this. Then we get a square root of this mean, which is 2.77, which is our standard deviation. So that's how basically we calculate the standard deviation. You have the series of numbers. You get the average of those numbers. Then you calculate the deviation from the average for all the numbers. Then you get the square of these deviations. You add them up, you get the mean. Then you get the square root of the means. So that would be your standard deviation. Any questions so far? So you know about basically standard deviation. You already seen the square, basically the equation of it. So I have a questions. Maybe some of you know that. I mentioned that if you get the sum of them, you're going to set 0. Okay, that's why basically I mentioned I'm going to get the square of them to make them basically positive numbers, so I don't have this problem. So why I don't get the absolute value only? But basically the question is why we do the square of the deviation, not the absolute value, for calculating the standard deviation. Anyone has anyone ever thought about it? I mean, of course, I guess I'm pretty sure. I guess you've seen this standard deviation in other courses. For all of this median, mean, median, and so you never had this question why we calculate the basically a square of the numbers, but not the absolute value of the numbers. Any answer? Okay, that's you can Google it. It's interesting. You see why basically for standard deviation we calculate the basically a square of the deviation. So anyway, you don't need to do all this calculation to calculate the standard deviation. You can just run call this function that we have NPSTD. Basically, it's calculating the standard deviations. But if you forgot this, now you know how to calculate the standard deviation for your data. Going back to the slides. So basically, this is what you get. Okay. This is the equation of it. The standard deviation basically measures roughly how far the data are from the average. So it is their standard deviation is the root mean of the square of deviation from the average. So it's a little bit confusing if you read it like this. Maybe the better way is like going reverse. It's basically the average of the deviation that you get. You do the squares of it, then You get the mean of it, then you calculate the root of it. The square root of it becomes basically your standard deviation. Okay. Any questions? So remember also a standard deviation has the same unit as the data. Hence, it's okay to say average plus or minus a few standard deviation. Okay, when I'm going to talk about this later before it gets more confusing. Let's see what we have in the table. So this is the same table that we saw earlier. Okay, basically the birth weight, maternal basic smoker, age, height, and all those information. I put it in this table. Table name is birth. So if we do the histogram in the maternal age, this is the age of the basically all the ages that we see here in maternal age. And if I take the mean of it, okay, this is the mean of this distribution. This is the median of the distribution. As we said, you remember we were talking about if the data is skewed to the right, to the higher numbers, so your mean going to be bigger than your median. So you can see here, this is skewed more towards the right, so the mean is slightly bigger than the median. So if I do the histogram for the birth weight, histogram for the maternal age, okay, so you have these two histogram. So I have this question for you. Which has a larger standard deviation? That's different. Deviation.
The birth weight.
Okay. Any guess?
I think birth weight should have the largest standard deviation.
Why is that?
Because there's more variation between each point in the data.
Okay. Okay, that's correct, I guess. Let's calculate it. Anyway, by looking at it, can you say what is the standard deviation just by looking at this histogram?
No, but since comparing the two histograms in birth weight, the values are more spread out and they are not like concentrated in a particular spot as much as they are in maternal age. In maternal age, the range of values is not as big, and most of the values are near a certain point. That's why I can somehow tell the difference in the standard deviation, but I have no idea of the quantity.
Perfect. Actually, the idea, the last thing that you said is correct, is like, actually what you expect usually for a standard deviation, you expect to see higher number when your data is not like a more like a normal distribution, is skewed towards left or right. You usually expect to see higher standard deviation, but in this particular case, as you highlighted correctly, in the left one, it should be bigger because of the range of the number is different. Not because of the shape of the distribution, but because of the range. Because usually in this type of distribution, skewed left, skewed right, you expect to see higher standard deviation, but here is just because of this series of numbers is bigger, so you see different number. So this is basically the results. If I do it, you can see a standard deviation for this one is 5.8, for this one is 18.3, It's bigger, not again, I'm highlighting here, saying that again, emphasizing on it, not because of the shape of the distribution, because usually in the shape like a normal distribution, you expect to see a smaller standard deviation than those skewed, but you also have to look at these numbers. Here is from 60 to 180, here is from like 15 to 45, that's it. So let's talk about, any questions so far? Let's talk about Chebyshev inequality. So why to use basically standard deviation at all? So no matter what's the shape of the distribution, the bulk of the data are in the average, in the range of average plus minus a few standard deviation. No matter what's the shape of your distribution, if you get the average of your data and plus minus a few standard deviation, for example, 1, 2, 3, you're going to get most of your data in this range, right? So Chebyshev inequality, inequality says no matter what the shape of the distribution, the proportion of value in the range would be in the range of basically average plus minus z standard deviation is at least 1 minus 1 over z to the power of 2. So if it's confusing, just look at this table. So this is your range, for example, average plus minus 2 standard deviation. In this one, you're going to have at least 75% of your data. If you have basically, if you consider 3 plus minus 3, you're going to have basically, you remember it was like 1 over z to the power of 2. Your z is like 3 here. So 1 over 9, basically 1 minus this, you're going to have 88.8% of your data in that range. Plus 4 this, plus 5 this. So remember, this is not for just normal distribution or whatever the distribution might look like. This Chebyshev inequality basically theorem would apply. So let's look at it in the data. This is the same table, paired table. Let's calculate average and standard deviation for my maternal age. So I'm looking at this maternal age. This is the basically average of this maternal age. The standard deviation here is 5.8. So if I do this, basically what here I'm calculating, I want to know the percentage of the basically, okay, let me remove this. Make it more clear. So what I'm doing here, I'm getting this third table and I'm saying where, look at this column 2, okay, where these values are between average, my average, minus 2 standard deviation. Remember, looking at the Chebyshev theorem, and plus minus 2 plus 2. If you look at this here, the table, I'm calculating this, okay? I'm looking at plus minus 2 standard deviation, my distribution. So I expect to see, this is the basically minimum, basically bottom part is like, I'm expecting to see at least 75% of my data falling in this basically range. So if I do this, this is the table, I'm getting that table. So if I basically take this, the number of here, okay, number of all this row that I have divided by the total, I'm going to get basically the percentage of my distribution between plus minus 2 standard deviation. So this, I have 95% of my data falling between average plus minus 2 standard deviation. According to Chebyshev rules, I'm going to see at least 75%, at least. It's not saying the maximum, it's saying you're going to see at least 75%. So what I observe is way beyond that. I observe 94%. So I wanted to show you the distribution. Turn your turn the smoker. Okay, yeah, I should drop the. It's fine. So if I run this, okay, what I'm doing here is I'm calculating the histogram for all these values. I drop this because it's just true false. So I draw a histogram for all these values. So if you run basically this histogram commands with overlay false, it's going to calculate, it's going to draw a histogram for all the value. If you don't put the overlay false, it's going to basically calculate and put them all on top of each other. So because I want to look at them individually, I put overlay false. So I get all this basic histogram for this, and this, for all these columns. Okay. So this is the maternal age. Let me look at the maternal age. This is the maternal age, right? So you can see it's not totally normal distribution. It's more like a skew towards right. Okay, so, but I see still this number, it's still a big number for considering the Chebyshev data, Chebyshev theorem. So if I, here in this piece of code, I'm calculating this value, okay, these numbers for all these columns, okay, with all the percentage. So if you look at this, it's like in the average, like this one was not part of basically Chebyshev rules, but it start from here. If I have my average and plus minus 2 standard deviation, in column 0, I get 94%. If I do that average plus minus 3, basically 3 distance from my standard deviation, I get 99%. So you can see here, considering this, the Chebyshev rule was telling us you have to see at least 75% of the value falling in this interval. But I can see here it's 95% here, 93% here, 94% here, 97% here, 95% here. It's a lot. Okay, so basically what I see, even when my data is not perfectly symmetrical, let's say, my shape, my histogram is not perfectly symmetrical or no normal distribution, still I see way bigger than Chebyshev inequality theorem, that it is expected to be 75%. Okay, so let's go back to the thing slide and see how we can use it. So let's talk about the standard unit. So what did, let me show you again. So what did so far here, okay, like if I go back to this, you remember I show you this, right? I show you this and I ask you which one has larger standard deviation? And maybe just by looking at it without so much care, you say, okay, the right one, the maternal age should have higher standard deviation because it's skewed more. But then you consider this, okay, now this two doesn't have the same value. This is the weight, this is the birth weight, this is the maternal age. So they are not the same value. So that's going to be a little bit problematic. So what we're going to do is we're going to have, no, sorry. We're going to, what was that? We're going to define the standard units, okay, to have the standard unit for all that distributions. So in order to calculate that, we can say how many standard deviations are data above the average, okay? So by just looking at this, we can define some standard unit that doesn't basically depends on the unit that we are saying. It's like a height, it's a weight, so what is it? So this is the standard unit, how many standard deviations we are above the average. So we usually refer to it as Z, so you calculate it like you have your value, you you minus mean, and you divide by the standard deviation. So you get basically the z value, which is a standard unit. If you get the negative z, the value are below average. Positive z, of course, means the value are above the average. If you get the z, 0 exactly, it means your value are exactly equal to the average. So so by the Chebyshev rules, most of the values of z are between -5 and 5. And also if you calculate the standard unit or z, then your average always would be 0 in this standard unit, and your standard deviation would be always 1. So your standard deviation will be always 1, considering the standard unit. Your average always be 0, and by Chebyshev rules, most of the units, most values of z are between -5 and 5. Let's see that in a basic code, looking at the same table. So what I'm doing here, I'm calculating the basically average standard deviation for my column 2, which is maternal age. So this is the same number that we saw, our average standard deviation. So what I'm going to do now, I'm going to calculate the standard unit for this. You remember the standard unit was value minus average divided by standard deviation. So if I calculated this, I get all this standard value. And if I put that in a table next to the value itself, so this is my value, original value from my table, maternal age. This is those value converted to the standard unit. Any questions so far? No? Okay, I hope you're getting what I'm talking about. I'm going a little bit fast maybe. So remember, I said the standard, we want to have the standard unit so we can compare basically two different values. If one value is based on the weight, one is age, you cannot basically do anything there, right? You cannot compare even the histogram because they are coming from different basically value. So that's why we can have this standard unit. We can calculate the standard unit, which was basically our value, which is like, for example, the age is 27, 33, 28. We get that value, we minus the average. Our average is this. And we divide that by our standard deviation, which is this. And we get our standard units. So if I do the histogram here, this is the histogram of a standard unit. This is the histogram of my actual data. Okay. So if you look at it, the distribution more or less look the same. It's not exactly the same, okay? But at least the pattern, like skewed, is still remain the same. It's skewed more towards the right, both of them. And here, as we mentioned, the average is 0 for this one. This is your average here, or your mean is falling here, and your standard deviation is 1 for this particular histogram. So let's now talk finally about normal distribution, the most common distribution that you're familiar with. So usually, as we mentioned earlier, I'm asking you, just looking at the histogram, can you calculate the standard deviation or not? You said it wouldn't be that easy just by looking at the histogram to calculate it. But if the histogram has a bell shape, then somehow you can estimate the standard deviation just by looking at the distribution of the histogram. So if the histogram is bell shaped, then the average is, you expect to see the mean or average at the center of the distribution. And the standard deviation is the distance between the average and the point of inflection on either side. Let's see what we mean by that. If we get this histogram for basically this one, the column 3, which is maternal height. This is for maternal height, okay? So you can see this is not perfectly normal distribution, but it is a bell shape, kind of normal distribution. At least you can say it's a bell shape, okay? So by looking at it, what can you tell me about the standard deviation? Looking at this, you can say that your basically average is here, right? Average is around 64. And we said the standard deviation can be the distance between the average, which is this one, and the point of inflection on either side. Basically, the point that the pattern of the data start changing. Anyone can tell me, or estimate, not exactly standard deviation, but estimate the standard deviation just by looking at this? Yes, no?
1?
That's, someone told me 2, someone said 1. 2 is closer, I assume. Because, okay, what you can say here, what you can do, let me see if I can draw something here. This is basically the way that the data is growing. Okay, if I connect these lines with each other. Okay. Let's see if I connect these lines together. I had to connect the other side, but anyway, if I connect this, you see this is basically the distribution here. Here, the data here is increasing. Basically the maternal height here it's increasing faster. You can see a bigger jump here, but suddenly at this point, okay, it start increasing slower till it's basically changed the pattern totally. Going again, falling fast here, then it gets slower. So looking at this, maybe you expect to have the standard deviation somewhere around this point. This is your average, your average or your mean, which is 64. You say this is around 67 something maybe, okay? Then you minus this, you say my the standard deviation should be around 2 point something, I assume. In order to see, we calculate and see how much we are right. As I mentioned, if it's bell shape, so the average is in the center, 64. And the standard deviation would be 2.52. So the same thing that we said, like we could estimate it more or less. So you get it? So basically this is the point that point of inflection of data in either side, in this side or this side, when you basically see the pattern of this jump, this changing suddenly from here, it's basically growing. At this time it's become like linear a little bit, then start going down, more or less, okay? So let me remove this annotation. So let me see what I did here. I don't remember really. Okay, this is basically what I did here is I'm doing 1 million random samples. Okay, calling my random functions, which is basically a normal distribution, getting basically a sample from normal distribution 1 million times. So this can be basically a theoretical normal distribution, a perfect bell shape or a perfect normal distribution. Not perfect, not very perfect, because still I'm doing the random sampling from a normal distribution, but I do it a million times, so you can see this is a more or less a perfect normal distribution. Basically hanging around the 0 here. So let's see how many slides I left. So okay, let me go. Or Now let me continue so we can finish earlier. So I don't want to give you a break and come back 5 minutes and then I talk 10 minutes. So let's finish and basically finish everything up to this point. So let's talk about normal distribution. And we talk about this, did this. So, sorry. So no matter what's the shape of the distribution, we saw this, the bulk of the data are in the range of average plus minus a few standard deviation. That was Chebyshev basically theorem or rules. But if the histogram is bell-shaped, then almost all of the data are in the range of average plus minus 3 standard deviation. Remember that for basically for this was the for all the distribution that based on the Chebyshev rule was you get average plus minus 1, you get at least 0%. For average plus 2 standard deviation, you have at least 75%. Average plus minus 3 standard deviation, you have at least 88.8%. This is for all type of distribution, no matter what is the shape of your distribution. This is for normal distribution. For normal distribution, average plus minus 2 standard deviation, you get about 95% of the data. If you remember this one, we get around 95% of basically the data in with the 2 standard deviation away from our average. So even if you look at this, maybe this is look like a normal distribution. This is kind of, but this not. But still we get close to 95%. This is look like not perfectly, but still we get 95%. Basically, just 2 standard deviation away from our average. So that basically leads us to central limit theorem, which tells us if a sample is large and drawn at random with replacement, then regardless of the distribution of the population, the probability distribution of the sample sum or the sample average is going to be roughly bell-shaped. So it is a very interesting observation actually. This central theorem is very interesting observation. It tells you if the sample is large and drawn at random with replacement, regardless of what type of distribution you have in your population, the probability distribution of the sample sum, or let's say sample average or whatever, going to be roughly bell-shaped. Let's go back and see if that's really applies. Let's look at histogram of maternal age. Let's take the mean of the maternal age. This is the mean. This is what I'm doing here. I'm getting the maternal age. I'm looking at my table, the birds. I'm looking at these birds. I'm looking at my maternal age. I did the histogram. I'm doing basically, I take the mean of that. Here, I'm doing the sampling from that, okay? You remember these functions that it does a sample with equal size replacement true. I'm taking the sample, then I'm calculating the mean again. So this is the mean from my original table. This is the mean from my sample, okay? So what I want to do that, like 10,000 times. I want to basically take the samples, draw the mean, take the samples, draw the mean, take the samples, draw the mean, and then I want to draw that in a histogram, and I want to see if the central theorem limits is really applies to this. Let's see. It's taking too long. It shouldn't be this long. Anyway, okay, so what I did here, I did it like 10,000 times. I take the sample from my maternal age, same amount of samples with a replacement true. I take the samples, I calculate the mean, And I draw here that, how to say, the histogram of it. So you can see the central theorem limits was telling us, regardless of the distribution, you can see this is not a bell shape at all. So regardless of what type of distribution you have here, if you basically, the probability distribution of the sample mean going to be roughly bell shape. Any questions so far? So this central theorem limits basically make it possible to make basically some conclusion, okay, with very little knowledge about the population that we have. Okay, so if we have a large random samples, if we have large random samples, we can take some, basically, we can get some conclusion regardless of our original population. Okay, is it, again, that's the whole idea. That's why they call it basically central theorem limits, central limit theorem. Basically, it means it's a center of the field of the statistical, basically, conclusion or the statistical inference. So if I make it smaller, if I run it like 100 times only, this is what I get. That's what we are talking about, the big number. If I run it 10,000 times, this is what I get. So as I'm increasing that, I'm getting more bell-shaped distribution, regardless of what is my original distribution. This is very interesting, actually, observation. Later, you're going to see this more. That's actually, that's why we call it like central limit theorem, because it's a central and it's very important in the field of basically statistical inference. Any questions so far? Is that all clear? All good? Okay, perfect. So let's finish it here. Any questions? So no questions. I'm stopping recording. So.